Okay. Okay, so let's go back to our lecture notes. Okay, so I had the 4s2. Okay. Okay, so 4s2, and then you go across and covers 1, 2, 3, 4, 5, 6, 7, 8, 9. 3. Oh, I'm sorry. I had it on no color. Oh my God. 3D. What is that? I said 9, right? Okay, that's what I said. This is what we taught you when you were in Chem, Intro Chem and 111A. Okay, so that's what we're going to put for right now. However, if you can see, oh, yeah. I'm not done. Okay. Okay, so this is what I'm telling you. We did not want your brains to, how can I put this? Okay, okay, let me just finish. This is what we taught you. This is what most professors will teach the students in chem and intro chem, especially in intro chem, where they can just barely do the electron configuration. And a lot of professors in 111A also teach them. But we lied to you because we didn't feel you could handle the truth. If you look on the screen here, you can see that what actually happens is you fill up the d orbital. So what happens is one of the electrons here in the s orbital goes into the d orbital, because then you will have a complete d orbital. It's more stable to have a complete d orbital. Okay, so this is what we taught you, especially in intro chem, when you were just learning how to do these electron configurations. This is what we taught you. So basically, we lie to you a lot, and then when you take more chemistry, you realize it's more complicated, and then we tell you the truth. So this is the truth. And it's because it's more stable. Okay, so I believe that, yes, so yes, all right. Okay, so then if you're going to take away electrons, then you get the ion. So you would end up taking away one electron here and one electron here. So that's how you get the ions. Please tell me I did that right. Somehow I just didn't. Okay. So what do we end up with if we take away what we're essentially taking away 1, 2, isn't that 3d10? D10. So this is common, well, not common, but this happens sometimes, that you would predict this electron configuration for copper, but in actuality, because the energy states are so close together, that you can move an electron from the s orbital into the d orbital, and then more stable, and you always want to go to more stability. So the transition metals are metals. I mean, they're in the metal place. They typically have high melting points, high boiling points. They're hard solids, except for the 2B column. Except for the 3B and the 2B, there's lots of different oxidation states, and a lot of them are colored compounds. And they conduct electricity well.
Professor?
Yes.
I have a question about this one. Like if we take 2 electron, then it should be 3D9 or 3D4.
Oh my God. Yes, you're right. Oh, where is my brain? I was thinking it in my head. I don't know why I typed it different. Thank you so much. You're correct. Okay. Okay, so any other, did you guys get this copied down? Okay, so let me clear my doodles. Clear my screen. Okay. And then okay, so these are the lecture notes that I made over the summer when there were no students present, which is why he must have already watched it. Okay. And then let's go ahead and watch one of the real short Jove. They're so good. Just take a moment. Wow, that's taking a long time. Huh. Huh. Of course, it worked really well yesterday. That's Sunday, and then no one on the West Coast is using their computers on Sunday.
Transition metals are a group of elements located in the D block. They are placed between the main group elements and exhibit unique characteristics, such as,
oh my God.
electrical conductivity, colors, hardness, high melting points, and magnetism. Many of these characteristics are attributed to the filling of d orbitals. Moving across the period, electrons are added following the Aufbau principle. However, the outermost s orbital is filled first before the electron enters the n-1 d subshell, with some exceptions. Chromium and copper have a half-filled s orbital because it is energetically more favored to have a half-filled or full d subshell. The atomic size of transition metals decreases slightly across a period. As the electrons enter the d subshell, the number of valence electrons in the outermost s orbital remains steady, leading to an overall constant nuclear charge. Down the column, the trend increases from the 4th to the 5th period, but not below. The 6th period contains 14 additional elements of the lanthanide series, where electrons enter the n-2 f subshell before entering the n-1 d subshell. Electrons located in the f orbitals do not sufficiently shield the valence electrons in the outermost s orbital, resulting in an increased effective nuclear charge. Thus, the valence electrons are attracted more strongly, leading to smaller than expected atomic radii. This is known as the Lanthanide contraction. Similarly, the transition element's electronegativity is influenced by its atomic size and nuclear charge. Moving across a period, it increases only slightly. Down the column, the electronegativity increases from the 4th to the 5th period, but remains constant in the 6th period. This is attributed to a decrease in atomic size and an increase in the nuclear charge. The ionization energy of transition metals increases slightly across a period. Interestingly, down the column, it is higher for the 6th period than for the 4th and 5th periods. Here, the valence electrons are held more tightly as the nuclear charge increases with a negligible increase in atomic size. Lastly, transition metals can have a range of stable oxidation states by losing outermost s orbital electrons before the unpaired d orbital electrons. The partially filled d orbitals enable oxidation states ranging from +7 to +1, characteristic colors, and magnetic properties.
Okay, enough of that. Okay, let's go back to the lecture notes. Okay, so they discussed the Aufbau principle, which is the filling up. And then we said we've got exceptions. And so if we're trying to understand the exceptions and explain them, this is the why of it. For chromium, to have filled sub levels is a lower energy state than having the S filled. For copper, a filled D sublevel and a half filled sublevel is more stable than having the S filled.
Professor,
Yes.
I have a question like what about the element in the same group of copper like silver or gold? Are they also the exception or only copper and chromium?
Okay. I think I gave you, ooh, what chapter is that? That might be way back chapter. Okay, I don't want to just make up something because I try to give you the most common exceptions. There's not a lot of them. So that's going back to chapter 7. Okay, so chapter 7, page 301. Okay. Oh. Oh, okay. Okay, so to answer that question, you're probably going to have to use the ebook. And you're going to want to go back to table, oopsie. Table 7.3 in the ebook, or if you have your physical book, that's in the Chang book. Okay, so you asked about silver. So let me take a look at silver. Where is silver?
Below copper.
Yeah, I think on my periodic table. I don't remember the. Oh my God, my book just fell on the floor. Oh, so number 47. Okay, well, I have to get my book because it's all on the floor now. I have too many items on my desk. Okay, so it's table 7.3. So if you have your actual physical book, you can look at table 7.3. If not, later you're going to have to look in your ebook because we're going back to Chem 111A. Oh, here we go. Okay. Okay, so you're asking about silver, which is 47. Oopsie, I went too far. Okay. Ooh. This would be such a good question on your final. It's too bad I'm done with your final. Okay. Oh, I got room up here. Okay, so let me do silver. Okay, so silver, which is number 47. Okay, that's going to be krypton. So electron configuration all the way up to including krypton. And 5s. Oh, I can't do uppercase on this thingy. I'll just go like that. So 5s1. Oopsie. Let me give us a space. 4d. 10. Okay, so there's your silver. And then you also asked about gold.
Yeah.
You also wondered about gold. Okay, so gold is 79. So let me give me some space here. Okay. Okay, so gold, 79. So that would be, ooh, okay, so that includes xenon. And then 6s1. Oh my God, 4f, what is that? 14. And then, oh, I should leave space in there. It's too hard to see otherwise. 6s1. Okay, there, that's better. Okay. 4s14. And then 5d10. Okay. Okay, so then what is the answer to your question?
Yeah.
Yep. Okay, and here's the why of it. If you have a choice, make the D full. That is more stable. So the why of this is a full D orbital is more stable than a full S orbital. Yeah, so if you have the option, then yes, you want to have a full D orbital. And it has to do with more stable and lower energy state. If you have a lower energy state, that's where you go. Like whenever you have the option of getting to a lower energy state, go there. If you have an option of getting a full D or a half full D, go there. Okay, does anyone need more time copying the doodles down? I think I'll put the bookmark in here. Okay. I'm going to clear the screen unless someone hollers. Okay. Wait.
Oh, someone in the, oh, never mind.
What? Did you holler? What happened?
Someone in the chat asked for more time, but
Oh!
yeah.
Man, I'm so, how do I get this thingies back? Oh, redo. Oh, I didn't redo it. Son of a. Okay, well, it's in your Chang textbook. I thought I could. Oh! Med has showed that to me. I have a mentee on the Tuesday, Thursday class. She's a PhD and she wants to teach and she showed me how to do that. I'm like, oh, cool. Okay, so you can just put in the chat when you're done. Wait, no, I fixed it. It's there, I found it again. It's only taking me a year to learn all this. You guys are so lucky you were in the class a year ago. I felt so bad for them. I was trying, but anyway. Okay, so you can put in the chat when you're done, because I know how to get to the chat from here. Wait, that would be such a good question to put on a multiple choice. Yeah, there is a tendency if you're in the same column for the same chemical reactions, and the chemical reactions come from the electron configurations. Yeah. Oh, what just happened? Oh, I think I moved it. Okay, so just put in the chat when you're done. Oh, good, good, good. Okay. Okay, so now let me clear it. Okay. Okay, so this is what happens when you're losing electrons. Typically, the s orbital electrons are lost before the d orbital electrons. And so you have a question here, and you're supposed to do the orbital box diagrams. That's where you drew like little squares and fill them in, and you do arrows going up and arrows going down to indicate the electron spin. And so what you're supposed to do in this question is you're supposed to do this little orbital box diagram for manganese atom, manganese ion 2 plus 2, manganese ion plus 4, and manganese ion plus 7. So that's what you're supposed to do right now. And just to kind of give you an idea, you would do like a box. I'll just go way back to the beginning. Wait, are there boxes on here? Kind of. Okay. So you do a box. Ooh. So 1s, 2s, 2p. So the boxes represent the orbitals, and you can start with the nearest noble gas. But this is how you did it. Like this is the 1s. This is the 2s. These are the 2p's. Like there's a 2px, a 2py, 2pz. We'll just put them all together. And you guys can start with the nearest noble gas, which is what we did here. Instead of starting all the way at the beginning, you can start at the nearest noble gas to manganese. So you're going to have to pull out your periodic table and figure out the nearest noble gas to manganese. And then you're doing this little box diagram. So that's what you're doing right now. So I'll give you some time to do that. Oh, that's too big. Okay, I'm assuming that you're working on this while I'm doodling, just to kind of show you. This is just an example. Okay, so that's what you're doing for manganese atom. So this is the atom. So you're doing this for manganese atom, manganese plus 2, manganese plus 4, manganese plus 7. And then you're going to pick which 2 would be the most stable. So that's what you're doing. You're answering the question. Okay, so you can see this is the manganese atom. You have to start from the manganese atom and figure out how to get the Mn plus 2, Mn plus 4, Mn plus 7. And then you pick the 2 most stable. Okay, there's the Mn plus 2. And we said you want to try to keep the half-filled d orbital is stable. So we try to keep that. So that's why we lost these. Lost.
So Mn plus 2 is even better than Mn?
No.
Or
Okay, so what we're saying is a full s orbital is stable. Okay, so this is stable.
a 4s orbital without anything is not as stable?
Well, there's nothing there. I mean, there's and this is stable. Okay, so here's our options. What we're saying is, okay, here's the question. Okay, you're going to start with the Mn atom. And then which 2 electrons should be removed? Oh, dang it. Okay, let me take, okay. So this is what you're, okay, start with atom. Electron configuration of atom. This is what you do for all of them. Always start with the electron configuration of atom. In this case, which 2 electrons do you remove? Okay, so that's what we're looking at here. So we start with this. If we remove these 2, then you would have this. So you would have a full s orbital, but not a half-filled d. That's not the best option. The best option is remove these 2. Because then we have this. That's a better option. That's a more stable. The Mn plus 2 is this, end of story. And the 3D half fold is stable. So instead of taking these 2, we take these 2 because that would be more stable. We're not going to go to less stable. We're going to go to more stable. That's how we figure out the electron configuration of the Mn plus 2. If we go back to the Mn and have to take away 4 electrons, that's how we get from the atom to the Mn plus 4. It's not more stable than the Mn plus 2. Mn plus 4 is not more stable than Mn plus 2. And then we have the Mn plus 7. So 1, 2, 3. Oh. So we need to remove 1, 2, 3, 4, 5, 6, 7. We need to move all of them. And then we get this, which is isoelectronic with argon. That is a word used in Chem 111A. It means it has the same electron configuration as argon. So we do all of this, and that's how we choose the most stable. So which 2 are likely to be the most stable? The Mn plus 2 and the Mn plus 7, based on the electron configuration.
Professor?
Yeah.
So which one is the most stable?
Well, there you would, okay. Okay, this would have a lower energy state. It would be this one.
Okay, so noble
Yeah,
gas.
because remember how stable the noble gases are?
Yeah.
Yeah, it would be this one. If you had to choose this over this one, that would be such a tricky question. I would never ask you that. You would have to remember that the noble gases are the most stable. That'd be such a good question though. Maybe I'll use that in the fall. Yeah, that would be a nasty question. Oh, if I gave you as a multiple choice question. Yeah, if I asked that to you, which I haven't, you'd have to pick this one because the noble gases. That would be so nasty.
So, which would be the second most stable? Would it be the
This
first one?
No, this
I'll
one.
be that one.
Yeah, this one. I mean, the atom
Okay.
is most stable of all.
Hmm.
That would be tricky though. But anyway, yeah, this one would be second because it's got a half filled. Half filled D is stable. I would not ask you guys to put them in sequence. So that would be so nasty. I would never do that. Not at this level. I mean, this is general chemistry. It's not like quantum chemistry. It's a whole nother class. Okay, the video kind of went over this. There's something called an effective nuclear charge. It's the positive charge felt by the electron rather than the actual, and increases going across a period. So what happens is the outer electrons are pulled in more as the effective nuclear charge increases, and then the orbital gets smaller, and so the covalent radii decrease. Okay, so this is the explanation of effective nuclear charge. It's the positive charge felt by the electron. It's the pull felt by the valence electrons. It's less than the full positive charge due to shielding or screening by inner electrons. Ooh, now we're gonna look at chromium. So we got colored compounds. That's how the Greek got, like the chromium got named from the Greek. Okay, you don't need to know what color is which. This is just some examples. So it just shows you that different compounds have different colors. Okay, so this is just a few examples of reactions. This is the ore, which would be in the rock. You have to have 1,100 degrees Celsius. You would get a sodium chromate, an iron oxide, and carbon dioxide gas. So this is a typical reaction that you would undergo. This just kind of shows you could do an experiment where you add acid and base and you could see the color change. And so you would know if you had the chromium oxide that's the yellow versus this compound, because you could tell from the colors. Okay, so you could identify, if you saw this color, you could say, oh, I have this compound. But if you saw it was a different color, it's orange instead, you would say, oh, I have this one. So in the lab, you could do experiments where you could determine which chromium you have, which chromium compound you have. And this would be a typical Le Chatelier type question that you would do in the laboratory. And based on the color, you would know where the equilibrium lies. Okay, copper, it's stable. And there's two ores where you would get the copper from. One of them is an oxide and one of them is a sulfide ore. You don't need to know those names. That's like a geology class question. Oopsie. Okay, so yep, we use it in coins, although we shouldn't be using it because the copper in the coin, like if you have full copper, that costs more than a penny. And that's why now you got zinc in the middle, coated with copper. We should just get rid of pennies. Okay, this is a test you will do when you take biochemistry. It's named after a person. Benedict's test. Okay, so this is what it looks like. Okay, so when you get to organic chemistry, you're gonna do this because people don't feel like drawing all the carbons. That's a carbon, that's a carbon, that's a carbon, that's one, two, three, four, five, six. Okay. And then people don't feel like drawing the H. You'll get used to this. You will come to appreciate it. People don't feel like drawing all the H's. So we understand they're there, and then we know this one's got, here we go. Okay, so Benedict's test is basic with a copper plus 2 is a real pretty blue-green. And then you can see what happens here. This is going to be the reaction right here, just on this first carbon. And then you can see this at the bottom of the test tube. And that tells you that you did have this oxidation reaction. This double bond O went to a double bond O with another O. And so you could do this with urine samples. And if you saw too much glucose in the urine, then you would have the condition glucosuria. Oh, I forgot an H. See, we didn't do anything to the alcohol groups. These are alcohol groups. So we've got alcohol. We still see they're still the same. So you see a nice color change. And hopefully you see enough of this in the bottom of your test tube. It's a direct proportion. So the amount of red precipitate is how much glucose. Electro refining, that was your question today, I believe. Electro refining is a process where you would oxidize the copper and dissolve it and then reduce it back to get pure copper. Ooh. So this is pretty much what was in your last chapter. And this is just a matter of setting up all of the units. So I'll give you some time to copy that down.
This is the question 5 on the quiz, right?
I don't know, is this just a similar question? I don't think I gave you the same one.
Well, different numbers, but
Yeah,
like
different.
the
Well,
same.
it's the same idea. Yeah, see, this chapter is talking about copper, but the process is what happened in the last chapter. So yeah, you're right. It's the same process. This is electro refining. So because they're telling you this is how many amps they use. So this is a way that you could make copper. Oh wait, I'm not done, am I? Sorry. Oh yeah. Oh yeah, I wasn't even done. There you go. So yeah, it's the last chapter was all about electrochemistry, but this chapter is talking about specific compounds, and it just happened to be copper. Yeah, this is different numbers. In other words, we're using a concept from a prior chapter. Used was aluminum. Okay, and this you would know that the copper, this one you would figure copper tends to go to copper plus 2 plus 2 electrons. So you would have to know that. But yeah, you're right. This is electrochem, but specifically for copper, because copper is a transition metal. Okay, does anyone need more time to copy that down? Yes. No problem. Okay, so I'm going to go ahead and stop the recording, then I'll start it again.